let's continue to look at how we work with data declarations for so-called inductive families. So we're looking at the less than relation, which is defined by these two constructors. And let's prove that this is actually a partial order. So it's reflexive, transitive, and antisymmetric. And we'll remind ourselves what these things mean when we get to them. So reflexive means that every element is related to itself, right? So n is smaller than or equal to n. And this is very similar to what we proved up here, that n is smaller than suc of n for every n. And we do it in the same way. We have to pattern match on the n, otherwise we don't know which constructor to use. So let's pattern match on the n. Okay, here we have to prove that 0 is less than 0, but we remember that there was one constructor for this, that 0 is less than anything, so we can use that one. And here we have to show that suc n is smaller than suc n, but we had a constructor for showing that suc something is smaller than suc something. So if we use that, then we have to show that n is smaller than n again, which is exactly what the recursive call would do for us. Right. Okay, so that's not so hard. Next on the agenda is to show that this relation is transitive. So if n is smaller than m, and if m is smaller than k, then n is smaller than k. Right. Okay, and here there's actually some choices, right? Because we have a proof p that n is smaller than m, and we have a proof q that m is smaller than k, and we have these n, m, and k, and a priori we could pattern match on any of these to make progress, right? And if we choose the wrong one, then we're going to have a bad time. It's going to be messy, and it might be worth taking a step back and trying again if you try to do these things and it doesn't work out. So how do we think about this? Well, in the end, we want to show that n is smaller than k. Okay, and this thing kind of makes a distinction on the lower number if it's 0 or a successor, right? So it makes sense that we want to make a difference on the lower number, but it's often a good idea not to pattern match directly on the numbers, because now we can pattern match on the proofs, and it's better to let the proofs limit what the numbers can possibly be, like we saw up here, right? We pattern match on the proof and we saw that the number could only be 0. But so what we should do here is it's probably a good idea to look at a corresponding proof that talks about n, which would be p. Right? So let's pattern match on the p, and we see that this could either be a 0 less than n, or it could be a successor less than successor proof. And what we have learned here is that if this is this one, then n must have been 0 to start with, right? Which means so we have this more refined goal, and we can use the same proof that 0 is less than n in order to prove this. On the other hand, if we're in this case where p was a successor smaller than successor, then we know that m must have been successor of n for something, and m must have been successor of m for some m. So now we don't quite know how to produce this thing yet, right? But we can still pattern match on the q, and we see that q at the moment is a proof that successor of n is smaller than k. So if we pattern match on q, we see that there's only one thing this q could possibly be. It has to be a successor smaller than a successor. We don't have to worry about it being this one, because this one is not of the form successor of n smaller than something. So we only dealt with this case, which means that we're now in a very lucky situation where first of all we have to prove that successor something is smaller than successor something. Well, we know how to do that. And secondly, we have exactly a p and a q that have peeled off a successor each on both sides. So we can do a recursive call on the p and the q. Okay, so that looked very smooth and very easy, but it's only because I did the right thing and pattern matched on the first proof. If I started pattern matching on the second one first, then I would have had a horrible time. So it's not always as easy as it looks. Okay, finally let's show that this relation is antisymmetric, which means that if n is smaller than m, and if m is smaller than n, so they're both smaller than each other, then they must be the same number. So we know that it's reflexive, so we can't say that this is impossible, that it's symmetric, but we can say that the only case where it's possible that they are both smaller than each other is if they are the same number. Okay, so how do we do this? Well, let's pattern match on the p again. Okay, so in this situation, let's see what we have. We now have a proof q that m is smaller than 0. What could that q possibly be? Well, it has to be another one of these. Okay, which means that we now have to prove that 0 is equal to 0. Right. It's a bit magical, but because we could only consider these two constructors, that meant that all the numbers involved must have been 0. So this one said that n must have been 0, and this one said that m must have been 0, which means that they are both 0 and they are both equal. Right. What about in this case? So here the first one was a successor less than successor, and the second one, we don't know what it is yet, but it has this shape. So if you pattern match on it, then I have a feeling for what it could possibly be. Yes, it has to be a successor less than successor again. Right. So now we have to show that, so that has told us that this one told us that n was a successor, and this one now tells us that m is a successor as well, which means that we now have to show that one successor is equal to another successor. So if we do a Kong of suc, that means that we just have to prove that the something is equal to something, m is equal to n, but we can do that with a recursive call as well, right? Because we've now peeled off exactly the right things that we need for this. Okay, so what have we learned? That's for the next video. The main takeaway here is that pattern matching on constructors for inductive families reveals information about other patterns, which is really useful, such as here, for example, where we pattern matched on these constructors, which told us things about the n and the m, that they both had to be 0 here and that they both had to be successor here. So this is the real power of these so-called inductive families, and they're really, really powerful and really fun to play with.